Welcome to this video on direct air carbon dioxide capture and carbon dioxide removal. We will explore negative emission technologies, ocean alkalinity, and the frontiers of global scaling for these critical climate solutions. Prepared by Dr. Qureshi from National University of Singapore. In this video, we will examine the learning objectives, including the deconstruction of direct air capture, an evaluation of BECCS and weathering, and an analysis of MRV and permanent standards. Next, we will discuss the physics of atmospheric dilution and its implications for direct air capture technologies. Understanding the differences between point source carbon capture and DACCS physics is essential. Point source streams have much higher concentrations, while atmospheric streams are ultra-dilute, requiring massive air movement. The quote, atmospheric entropy penalty describes why extracting CO₂ from the air is so energy-intensive. It requires significantly more thermodynamic work than flue gas, often 10 times the theoretical minimum. This equation illustrates the minimum work of separation, governed by the Gibbs free energy of mixing for dilute ideal gas solutions. Dilution directly influences thermal regeneration limits. Direct air capture systems utilize modular fan arrays to move air across contactors. A key advantage is, quote, siting agility, as these facilities can be placed directly over storage sites to avoid complex transport. Engineering approaches differ between solid sorbent and liquid solvent DACS. Solid systems typically use low-grade waste heat, while liquid systems require high-temperature processes for regeneration. This matrix compares key parameters for these DACCS technologies, including regeneration temperatures, primary energy sources, water consumption, and land footprint requirements. Moving on to bioenergy with carbon capture and storage, or BECCS, and the role of biogenic sinks. The BECCS value chain begins with photosynthesis, where plants absorb atmospheric CO₂. By capturing and sequestering the emissions from biomass energy production, we can create a net negative carbon loop. Photosynthetic efficiency and supply chain emissions are critical to the net carbon balance of BECCS. Upstream activities like fertilizer production can reduce the net efficiency of the CDR process. Scaling BECCS presents significant footprint constraints. Large land areas are required, which can impact food security and biodiversity, necessitating a focus on sustainable biomass sources. This feedstock matrix outlines various biomass classes, their carbon density, sustainability risks, and the typical conversion routes for each. Finally, this video covers the foundations of enhanced weathering and marine carbon dioxide removal strategies. Enhanced rock weathering accelerates the natural geological carbon cycle by spreading crushed silicate rocks like basalt or olivine on croplands. This process reacts with atmospheric CO₂ to form stable bicarbonate ions in runoff. By grinding these rocks into a fine powder, we expand their reactive surface area by a factor of 10,000, turning a cycle that normally takes millions of years into a multi-year process, while also providing valuable agricultural nutrients. The chemistry of forced-right weathering is shown here. Theoretically, 1 ton of pure olivine can sequester up to 1.25 tons of atmospheric carbon dioxide, permanently trapping it in stable forms. Marine carbon dioxide removal, or MCDR, involves dispersing alkaline substances like lime or brucite into surface ocean waters. This process converts dissolved CO₂ into non-volatile bicarbonate, which aids in restoring ocean chemical equilibrium. Implementing marine CDR requires careful attention to safety, such as monitoring heavy metal traces in minerals, managing localized pH spikes, and developing sophisticated models for measuring carbon dispersion. Next, we will explore the critical requirements for carbon durability, measurement, reporting, and verification, and the concept of additionality. This chart shows the spectrum of carbon permanence. While afforestation faces risks of reversal over 10 to 100 years, enhanced weathering and mineralization offer geologic scale storage lasting over 10,000 years. A robust MRV framework relies on proving additionality, ensuring the removal would not have occurred under business as usual, and managing risks like secondary supply chain emissions or potential reversals. Net removal efficiency is calculated by subtracting total supply chain emissions, such as energy and transport, from the gross captured volume. Efficiency is heavily influenced by the carbon intensity of the local energy grid. Carbon registries play a pivotal role in the CDR ecosystem, ensuring transparency and credibility in how these removal activities are certified and traded. Now, let's examine the economics of CDR and the growing voluntary carbon market. Technology scaling and modular manufacturing are key drivers in reducing costs toward the $100 per ton target, as shown in this comparative cost analysis across different net emission technologies. Advanced market commitments provide essential support by guaranteeing future purchase volumes, which helps early-stage startups secure the financing needed for large-scale infrastructure. The U.S. Department of Energy's carbon shot target aims for $100 per ton of net removal. Achieving this will require cheap zero-carbon energy and optimized, high-cycle chemical processes. Thank you for watching this overview of global scaling pathways and the future portfolios for net zero carbon removal by 2050. We now look at the gigaton-scale CDR roadmap. By 2050, IPCC pathways demand 5 to 10 gigatons of annual carbon dioxide removal to offset hard-to-abate emissions in sectors like aviation and shipping. This goal necessitates building an industry with a physical mass handling capacity comparable to the current global oil and gas sector. Achieving this scale requires a balanced portfolio of diverse removal technologies. This chart presents the projected 2050 portfolio mix, detailing how different carbon dioxide removal archetypes contribute to the overall global sequestration requirements. This comparison matrix provides a detailed breakdown of different net emission technology archetypes, evaluating their unique characteristics and deployment potential. For further study, key references include reports from the National Academies, the IPCC, IEA GHG, and the U.S. Department of Energy, which offer foundational research and technical frameworks for carbon removal.